Okay, real quick. Okay, let me get everybody face the front, please. All right. What I've done here real quick, I have taken the problems that were the most problematic from the 1-2 assignment that's due tonight. Thanks, sir. And the 1.3 assignment that's due tomorrow night. And I pulled in some samples of those. So let's take just a quick look at these and make sure we don't have any issues, and then we'll move on to today's stuff. And then I think there'll be a little time left over. Okay, so what do we do with simplifying problems like this? Okay, we're going to do PEMDAS. Okay, we're going to go through our order of operations. Now, what's our general strategy? Travis, why don't you close that up for just a little bit here? What's our general strategy when we've got a bunch of junk on the top of a fraction and a bunch of junk on the bottom? What do we want to do? Sure.
Reduce it.
Okay, reduce the top to one number, right? Bottom to one number, and then the last step will just be see what we get when we divide them out. So let's deal with the top. Let's make that, how about blue? What can I do on the top of this? What's the first thing I'm going to do if I follow PEMDAS?
Exponents.
Exponents. Okay, so the 2 squared becomes a 4. Now what? 4 times 1 is 4, so I end up with 4 plus 26. That's pretty easy. What is that? 30. Okay, what about the bottom? Let's do the bottom. Bottom's going to be red. Okay, parentheses, but which ones? Okay, first meaning the inside ones. So I got to deal with those first, right? What do I do first in there? Okay, so the 3 squared becomes a 9 minus 8. What's that? 1. Okay, so now it looks like 5 times the quantity, 6 times 1. So technically, what do I do first? 6 times 1 is 6. Times 5? So what's our answer? Yeah. Okay? Good? All right. So there was one. That looked like not that big a deal. Fine with it. Okay, this one. Now I know what people are doing with this. If I look at the answers that I'm seeing that are incorrect, here's what people did. And I'm not sure, you got to tell me, well, I mean, I'll find out when I look at them, when I finally grade them, but I wonder if maybe this is another one of those problems that's just not behaving well, too. I think maybe some people are missing this just because it's not working well. Either way, you'll get credit. The problem people are having is, on the top, what do I obviously do first? Parentheses. 3 minus, and what do I do first in the parentheses? So I get 3 minus 15. What is that? 12. -12. Good, so that's all becoming -12. And what's 6 squared?
36.
Okay, so it's 36 minus -12, right? If people made a mistake on this, what they tend to do, and I don't know why, but it just tends to happen a lot, people tend to make that 36 minus 12. I think they just overlook the fact that you're subtracting a negative. But what is it really going to end up being? So it's not 24, it's 48, yeah. Subtracting a negative is adding. So we get 48 on the top. Now on the bottom, what am I going to get? 19. 24 plus -5 is 19, and that's how you should be able to enter it. Okay. And if it's not working, then you'll get credit for it. You know, like I say, those first 3 assignments are just kind of a disaster. We'll get through it, and then we're on to stuff that works. Okay. All right, this one. There's sort of a common theme in the next couple examples we're going to look at here. We want to take a situation, in this case a geometry situation, and turn it into an algebra expression. Turn it into an expression that represents area. So talk to me about that. What do we do? What do we do here? Isolate x. Okay, now isolate x is what we would do if we were solving for x. This is a little bit different. We're trying to write a simplified expression for area. So in other words, area equals something that's probably going to involve x's, right? How do we calculate the area of a triangle? Half base times height, right? So we know what the you might call it a verbal model even. That's what we'll call it today, later today. A verbal model. We know what we're trying to do with this. We just need to substitute in the algebra stuff for the words. Now, what represents base in this picture? What is the base? 16. Okay, so our area equals 1/2 times the base, which you're telling me is 16, times the height, which is what? Okay, now the x plus 3 has to be in parentheses, doesn't it? Right, because it's all that stuff, the x plus 3 is being grouped together to be one thing, one factor that's being multiplied, and that's the height. So if people made a mistake on this, this is typically where it was. They didn't contain the x plus 3 in parentheses to make it one thing, which is the height. So from here, it's pretty simple. Now, if I just simplify this from left to right, what do I get? What do I get first? 1/2 times 16 is 8, good. Times x plus 3, and then how do I multiply that? Distribute, sure. So I'm going to get 8x plus 24, right? And that's our answer. Okay. Is it weird that x's are in our answer? Well, I mean, maybe at first it seems a little strange, but isn't that almost to be expected in this case? If we've got this area and the height is dependent on x, as x gets bigger, what's that going to do to the height? Make it bigger, right? If the base is staying the same, but the height is getting bigger, wouldn't we expect that to change the area? Yeah, so that x really does need to be in there, doesn't it? Because we would say in math that the area is dependent on x. Makes sense that it would. As x changes, the area should change. So the area should be a formula involving x, right? Okay, good. All right, now what about this one? Let's take a look at this. I think this, I know when you look at the first thing probably you think it's, oh my gosh, shut down. Don't shut down. We're going to deal with these all year. The strategy for word problems is pretty much the same, always. We want to take that information that's very wordy and turn it into a real simple algebra expression. Right? We want to turn it into something that's very short and compact, and that's what math is good at. So it says here, in 1996, there were approximately 115,000 physical therapy jobs. Let's underline some key stuff here. So 115,000 physical therapy jobs. At that time, the number of jobs was expected to increase by 8,100 jobs each year. Okay? Write an algebra expression that predicts the number of physical therapy jobs. So it's going to look like this. Number of jobs equals each year starting in 1996 based on the data. Let the variable t represent the number of years since 1996. Now that's going to change, isn't it? Of course we need a variable in there because the number of jobs is going to change every year, right? How are we going to set that up? How are we going to start? Yes, ma'am.
115,000 is the number of jobs.
Okay, so that's what we're starting with, right? So we know that in 1996, that's how many jobs there were. Okay, is it going to stay that way? No, it's not going to. We got to be able to add another term up here that's going to correspond to the number that we're adding each year to our original amount. Now, what's that going to be? What's that going to be? That t must be important, right? Let's make the t red. How about t's got to be important because that's got to be the part that's going to incrementally make that bigger. Yes, sir. Yeah, good. Okay, now let's see why that makes sense. 8,100 times t. 8,100 is the number of jobs that we're adding each year, and t is the number of years since 1996. So what would the value of t be in 1997? 1, right? 1 year later. What would it be in 1999? 3, because that's 3 years after 1996, right? Doesn't that make sense? That's telling us the number of times that we're going to multiply 8,100 because that's how many years it's increased by that amount. Make sense? Okay?
It was 1, was that right?
What's that?
The first answer was 1.
You were right. You were right. Outstanding. Genius. Okay, so there we go. That's it. Okay, that's what we're looking for. Okay, what about this one? I like this one even better. This is a good example because it's giving us a situation that is geometry stuff. And it's asking us to solve for x, which is algebra stuff. So this illustrates what we do a lot of the times in math in kind of real life stuff. We're going to take a situation that is not inherently algebraic. We're going to rewrite that in a way that makes sense algebraically, and then we can just shift gears and go into algebra mode and just get an answer. We can kind of forget about the problem until we get an answer, and then we'll say, well, what does that mean? Well, now, in terms of our original problem, what does my answer mean, maybe? All right, so for the above figure, they're telling us it's a rectangle, right? The width is 15, and the length is 10x minus 21. So let's maybe add that stuff to our picture. So we've got a 15 and a 10x minus 21. Okay, they're telling us that the area is 428. They're telling us the value of the area. And the question is, what is x? Okay. So now think about this in algebra mode for a second. If I want to be able to solve for x, I need an equation involving x, right? And then I'll just isolate x in that equation. So what we've got to do is we've got to build an equation from this information. All right, so what's the geometry concept or relationship here that allows us to build an equation? Is there a way that we can link the length and the width of a rectangle to the given area? How are those concepts related in geometry? Length and width and area for a rectangle. I mean, what's the formula, if you will? I mean, that's all we're looking for. Length times width is area, right? Okay. So we want length times width equals area. That's good for us because we're given algebraic stuff that we can plug in for each of those things. We know that the length is this, right? So I can plug 10x minus 21 in for length. I know that the width is, new color here, the width is 15. So I can plug in 15 for W, right? And I know, last but not least, that the area is 428. So I can plug in 428 for area, right? Okay. And then we've got an algebra equation, and we can just forget about this stuff and shift into algebra mode. So what's that give us? Well, let's see. So we get 10x minus 21. Now, if I want to multiply that by 15, I have to write this down very carefully. What do I have to do? Got to have it in parentheses, because that's my length. It's all that stuff grouped together is length. Times 15 was 428, right? Now this becomes simple. This is just the same stuff we've been practicing. You've done this for years. What do we do to solve for x here? Okay, we'd want to distribute. Good. So if I distribute the 15, what's 15 times 10? 150, and then I have to have an x there, right? So 10x, that'd give me 150x. 15 times 21. Okay, now without using a calculator, how did you get that so fast? How do people, mental math is huge. This is something you gotta know about. The research all shows, if you look at metacognitive research, so how the brain actually learns the things. The same parts of the brain, if you look at a PET scan, which shows the brain actually in the process of thinking, the same parts of the brain that are used when you do algebra are active when you do mental math. And it makes sense to me because doing algebra, I mean, if you're doing mental math, you're actually doing algebraic things. You're actually grouping stuff and you're using properties. So it really does make sense. So as much as you can, I mean, force yourself to kind of do some mental math. So this is not that hard, but we got to learn to think in these ways. How do we multiply easily something like 15 times 21? What do you think? Yes, sir. Perfect. 15 times, we'll break it into 15 times 20 plus 15 times 1, right? And then it's going to end up being negative, but we just want to get the size of the number first. How do you do 15 times 20? Well, what's 15 times 2? 30. So if I'm multiplying by 20, I got to add another 0, 300, right? Plus 15 times 1 is just 15, so 315, right? So we get minus 315 equals 428. Now what are the two steps in order I would use to get that x by itself? Add 315, divide by 150, and we're there. So 150x equals, what am I gonna get? 743. Divide both sides by 150, and I get, who knows, some decimal. But we'll just round it. Tells you to round it. Okay. 4.95. Okay, so rounds to 4.95. What's that squiggly equal sign mean?
Not equal to or it's close to not equal.
Okay, so approximately. Yeah, that means we've rounded. That's not an exact answer, it's approximate. Okay? Questions on that? Make sense? Okay? All right, last one, let's take a quick look at. Okay, you guys quickly look at that, see what you come up with. Eric, go ahead. Hey. Yes. Yeah, it is. I'll call you in a little bit. Okay, bye. All right, so what about this here now? Let's look at this guy. During the course of a school year, a college student has 2 work-study jobs. First job, he works a total of 88 hours and earns $8.25 per hour. Second job, he earns $30 per hour, and that's all they tell us. If his goal is to earn a total of $2,886 during the year, how many hours must he work at the second job? Okay, now when you're reading a problem like this, you've probably been trained to do this, but what's the first thing you always kind of look for? If you want to know what you're supposed to do here, what do you, there's a bunch of information presented, but what's really probably the most important part of this whole thing, where we start? Okay, what we don't know, which is the question, right? We're looking for the unknown. So we're looking for the question. Well, there's the question mark. So we want to know how many hours did he work at the second job? That's the unknown. What do we do with unknowns? How's that going to look when we turn this into an algebra problem? That's the variable. Variable and unknown are interchangeable ideas, aren't they? So this is going to be the variable. Call it what you want. We'll just probably call it x. Okay. And now we've got to come up with some equation up here that's going to involve that x so we can isolate it and solve it. Yes, Yesenia, what do you think?
It's 2,886 equals.
Okay, good. Good. Let's start with that. Hold your thought. You're on the right track. So the total is 2,886 equals. Now, how are you going to do? Keep going.
I multiplied 80 hours and $8.25 per hour.
Okay, good. So let's pause there for a second. So 88 times 8.25. Here, I'll put it in parentheses. How about? Okay, now what does that represent? Good. What does that represent?
How many hours I went to the first job.
Okay, good. So that's this. Taken as a whole, this is really important that you kind of start to see things this way. This term right here is the money from, call it job 1, right? The number of hours he worked times the amount of money he made per hour, right? So that product tells us how much cash is he making from job 1. The total amount he makes is going to be the sum of job 1 and job 2, isn't it? Right? So what about job 2 then? Now keep going. I like this. Job 2.
X.
Ah, good. Okay, 30x. Because we don't know. It depends on how many hours he works, right? We know that at his second job, he's making $30 an hour. But x is the unknown here. That's the number of hours he works at the second job, right? Make sense? Okay, so there's our math equation, and now this becomes simple. We can shift into algebra mode, and it's no big deal, is it? What would we do to solve this? Yeah, I guess we probably want to find out what that number is. What is that number? Somebody? Say it again.
726.
So all that just becomes 726. Okay, we don't even need to finish it necessarily. I just want to know, what are the 2 steps you'd go through in order to solve for x now? Okay, first I gotta subtract 726, right? Then divide by 30, and then whatever answer I get, it's probably gonna be some decimal, but we can round it.
So it's 72, it's an even number.
Oh, it's an even number, how about that? So x equals, if we do that, we get 72, so there you go. That's the number of hours that he works at that second job, okay? Make sense? Okay. All right. Oops. Okay, very quickly, I wanna take you through, and this is, honestly, this is just gonna attach some vocabulary to the stuff that we just did. I don't mean for this to be comprehensive, this is nothing new, but in my experience teaching, this level, teaching Algebra 2, this is one of the things that people have the most trouble with is, and it's not, I mean, it's everybody, it's all, every place, I think it's just human nature, is taking word problems or real life problems and converting those into algebra situations that you can do something with mathematically. So let's just take a quick look, it's nothing new, but just kind of a refresher, think of it as, and how we can approach this. It helps us to have a verbal model, and we sort of have done that. What's the, we said, for example, that area was length times width, right, for a rectangle. There's a verbal model. Sometimes it's some other relationship, like maybe it's speed equals distance divided by time or something. We get some stuff like that. That's our verbal model. We'll attach some numbers from the problem and some unknowns from the problem that we're trying to solve to make it be algebraic, and then we can do all our algebra magic to get it done, okay? So a quick example. How about this guy here? We got a bullet train that goes between these two Japanese cities, total distance of 550 kilometers. When it makes no stops, we know it takes 2 hours and 15 minutes. So what would that be as a decimal, maybe, in terms of hours? 2 1/4, right? So 2.25 hours. What's the average speed of the bullet train? Well, what's the relationship we need here then? If we've got information that's given to us about distance and time, I don't know where it says time, but there's the time, and what we're trying to find, the unknown, is speed. What's our verbal model? What's the relationship between those things? How would that be? Distance. So we could call the speed, maybe you've heard it called rate. Distance equals what in terms of speed or rate in time? Yeah. Okay, distance, so that's one way we could do it. We could say that speed or rate equals distance over time. Another way you might have talked about it maybe in science or in other math classes is distance equals rate times time, something like that. But we need some kind of a relationship we can deal with. I think that's the one that the PowerPoint uses, so let's stick with that one. So distance equals rate times time, right? There's our verbal model. Now we just need to plug in the stuff that we know. Well, we know the distance, 550. We know the time, 2.25, and the rate is what we're looking for. So that's the unknown. We could call it X, or they call it R. It makes no difference. You got to call it something. That's our unknown. So we just plug that stuff into our algebra model now, the information that's given to us, and we get something very simple to deal with. That's a very simple algebra equation. What do I do to solve for R? Divide. Yeah, divide and I'm done, right? And so I get roughly 244, I guess it was kilometers per hour, right? Okay, no big deal. Let's look at one that's a little trickier and then I think we're done. Oh, this is kind of a good trick. And this is, my background's actually in physics, not in math, so this is right up my alley here. This is something that really, I think in science you see this a lot. How can you check to see if you did something correctly? One quick check. This isn't going to tell you if you did it right, but it'll certainly tell you if you did it wrong, if the units don't work out. If I'm trying to find, if I found the answer to be 244 kilometers per hour, if I plug this stuff into my original equation, distance equals rate times time, check to see that the units work. Well, they do, don't they? You treat units like variables. They cancel just like variables. So if I multiply kilometers per hour times hours, I've got hours on the top and hours on the bottom, and so they cancel algebraically, and what do you know? I get kilometers on the left and kilometers on the right, which is a pretty good sign that I did things correctly. No guarantee, but it's a pretty good sign. Just a little trick. Okay, sometimes it helps to draw a little diagram. Like, let's take a look at this. This is a little more involved problem. A little history for you here. So railroads. In 1862, there were two companies that were working together to build the what do they call it? Trans-something railroad, Transnational Railroad, I don't know. What does it say? Transcontinental? Maybe it's Transcontinental, there you go. So they're building a railroad from Nebraska to Sacramento. And then one company starting at one end, the other company starting at the other end, and they're just gonna meet someplace in the middle. All right, so here are the details. The Central Pacific Company began in Sacramento, and 24 months later, the Union Pacific Company began in Omaha, so they got a late start. They started at the other end. The Central Pacific Company averaged 8.75 miles of track per month. The Union Pacific Company averaged 20 miles per month. I guess these guys were going through the mountains, that's a little tougher. So there's the information. What we're trying to find then, if the total distance they covered was 1,590 miles, we want to know, first of all, in what year did they meet? Okay, and then if we know the year in which they met, we could pretty easily find out how many miles of track each company built. Okay, so let's, first of all, we just want to find when they met. So we got to set up some kind of a verbal model here. Well, isn't this pretty similar to the last one? I mean, it's different numbers and slightly different approach, but we're just looking at the distance that they cover equaling the rate at which they build track times the amount of time that they take, right? Does that make sense? So for example, the company that starts in Sacramento, the Central Pacific, if they're building track at a rate of 8.75 miles of track per month, then wouldn't 8.75 times X or T or whatever you want to call it, where that's the number of months, wouldn't that tell you how far they got, right? Rate times time would give you total distance. And the same thing for the Union Pacific, right? And the total distance, 1,590, must just be the sum of those two things. The amount built by Central Pacific plus the amount built by Union Pacific has to equal the total distance. Okay, so let's see if we can set that up. Should look kind of like that, wouldn't it? Okay. Total amount, miles per month for Central Pacific times the number of months that they built, plus miles per month for Union Pacific times the total number of months that they built. Well, the miles per month is, well, the total is 1,590. Miles per month for Central Pacific is 8.75. Number of months they worked, that's unknown. That's what we're trying to find. Let's call it T. Okay. What's the miles per month for Union Pacific? I think it was 20. Now, what about the number of months, though? Remember that we said that they started 24 months later. So if T represents the number of months that the Central Pacific got to build, T minus 24. Yeah, it's got to be this number minus 24 because they didn't get those first 24 months to build, right? Now, I can just plug that stuff up there and we've got an algebra problem that's not that hard, right? Now we can just forget about this and shift into algebra mode and solve that thing. So what do I do? Okay, good. I'll distribute 20. First step. Now what?
Combine like terms.
Combine like terms, so I can add the t terms up, and while I'm at it, if we want to skip a step, I could go ahead and add the 480 to the other side, couldn't I? Because we're really just trying to get the t's by themselves on the right. So I get something like that. Last step, divide. Okay, and it works out to be 72 months, so 6 years, I guess, right? So that's how long it took. Now, how could I go back and figure out how far, if I know that the total amount of time t was 72, how could I go back and find out how far Central Pacific went? That's this stuff. We found out that t was 72, right?
75 times 72.
Yeah, 8.75 times 72 gives us our answer, right? For the other company, Union Pacific is just gonna be 20 times 72 minus 24, whatever that is, right? And if we do all that stuff, it's, what do we get? 630 for Central Pacific and 960 for Union Pacific, right? Okay, very good. All right, now, how much time we got?